All right, so today we're going to be talking about asymptotic freedom. And as usual, I start with a review of lecture 16. We discussed non-abelian gauge theory in arc-C gauge. The Lagrangian that we're working with, the path integral we're working with, is a path integral over the gauge field. There is the fermion path integral. There's also the Gauss fields, right? So these are adjoint fields. For the gauge, they transform as an adjoint for the gauge transformation, and they're Lorentz scalars. These are Lorentz fermions, and they transform in some representation that I'll denote by little r. And then this is the gauge field. So there's the action. This is the gauge field. There's the Yang-Mills action for A. There's the gauge fixing term and the Gauss term. So here's the Yang-Mills term coupled to the fermions term. Then you have the gauge fixing term. We saw how it comes about in Fedya-Popov. And then here's the action for the Gauss fields. Integration by parts will turn this action for the Gauss into something more familiar, canonical, which is the kinetic term for the Gauss anti-Gauss plus an interaction term that couples the derivative of the anti-Gauss or Gauss to the gauge field. So this is a Gauss anti-Gauss vertex with the gauge field, the gauge boson. The Feynman rules are the propagator for the gauge boson is, of course, it's diagonal in the gauge indices, in the adjoint indices. So it's minus I over k squared plus I epsilon. It's massless. They have to be massless. And here's the fact that it has to be that there's no degree of freedom in the direction of the propagation of the gauge boson. So that this is coming from the inverse of the kinetic term, and then we're writing everything in the arc-C gauge. So there's 1 minus C here. The fermion propagator is the standard one. The Gauss one, as I said, is so it's diagonal in gauge indices, and also it's mass. The Gauss are massless scalars, so this is what it looks like. The Gauss anti-Gauss have a vertex with the gauge boson. The p mu comes from the fact that there's a derivative involved. And then we have the fermion antifermion that talk to the gauge field. There's this would be the representation. These are the representations of the fermion that decide this, right? And then there's gamma mu, of course, gamma matrices. So in SUN, TG and C2 of G are N. These are for adjoint representation. In the fundamental, T of N is half, and then C2 of N is N. Fundamental and fundamental is N squared minus 1 over 2N. If there are any questions at any point, please ask. We have two self-interaction vertices for the gauge boson. So orienting all the momenta inwards, we're going to end up with K mu minus P mu. This is P. My P's and rhos are sometimes hard to tell. And then we have Q minus K and then P minus Q, right? And then appropriate Minkowski metrics to contract them. Of course, there is one factor of FABC. It comes from the fact that from the expansion of F mu nu squared, the term that is quadratic, the term that's quartic, third power, has as third power in A will have one FABC. The fourth order term will have two FABCs and no derivative terms. So this is the structure of it. This is what the vertexes, and these are all the vertices in this theory. We talked about the BRC symmetry. We introduced a new commuting scalar field BA and wrote the action in this way. Path integrating over BA will give you back the gauge fixing term we had. Then we talked about a gauge transformation that is proportional to the Gauss. Gauss are anti-commuting degrees of freedom, so the coefficient for that has to be anti-commuting. The fact that the coefficient of that is anti-commuting, it tells you that if you do this transformation twice, the generator of this transformation is Q squared is 0, because epsilon squared is 0. that will be important. That's an important key component of the BRST symmetry and the idea of BRST. So the transformation of the gauge field and the fermion is basically given by by the laws of the gauge transformation. We pick BA to not transform, then the anti-ghost transformation is proportional to BA. Of course, this has to be a commuting field because this guy is anti-commuting and there's an anti-commuting epsilon. And then finally, delta CA is the second order, the ghost. All right. So this is a symmetry. We checked explicitly last time that this is a symmetry of the Fediev-Pavlov-Lagrangian. Structurally, the general structure is that the variation of every field is epsilon some q, a collection of fields acting on phi. Now, oh, sorry, I think. Yeah, now q squared of phi is 0. This is nilpotent, right? It comes from the fact that q is proportional to epsilon. And we're interested in gauge invariant states. These are gauge invariants. This is a gauge transformation. These states must be killed by Q. Now, all the states that are killed by Q could be written as a set of states that are killed by Q, but they are not Q of something, and the states that are Q of something, because Q squared is 0, Q of anything, if it's non-zero, will be killed by Q. So we call this Hilbert space H1 and this Hilbert space H0. We talked about the connection to homology, right? All right. So this was the BRC story. Now we start talking about non-abelian gauge theory at one loop. At one loop, we had the gauge boson, the 1pi propagator. We'll have the fermions running in the loop. We'll have the gauge boson running in the loop. This comes from the 3 gauge boson vertex. And then there will be this gauge boson loop coming from the 4 gauge boson vertex. And then there will be ghosts that will run in the loops. This is the gauge boson self-energy. This is the non-abelian version of vacuum polarization. We have fermion self-energy. Sorry, at the loop of the Feynman diagrams at this one loop. This is basically the same diagram as before. Now, of course, you have to keep track of the matrices that are now in the gauge generators that are the Lie algebraic structure of it. There is the boson-fermion interaction, which is this 1pi diagram. This is the diagram that we had in the past. What we called it in QED, we called it the vertex correction. Now there's another correction that looks like this. There are 3 counterterms. The counterterm that has to do with the vertex, the counterterm that has to do with the fermion self-energy, and the counterterm that has to do with the gauge boson. And there's the form of them, this is proportional to P slash, that's decided by symmetries. Similarly here, it's just the fact that it has to be the propagator has to remain transverse and diagonal in the gauge degrees of freedom. All right, so the gauge boson self-energy, each of the 4 diagrams has the form, which is Ig squared over 2pi squared, something diagonal and then transverse, integral. So this is, I'm writing this in x equals 0 gauge. Integral over d of x, gamma of 2 minus d over 2 over delta to the power of 2 minus d over 2. So this is the log divergent term in the dim reg. We also talked about more divergent term that comes up from the that in the past was showing lambda squared divergence. That's a harsher divergence, not log divergence. And dim reg, it shows itself as a pole and d equal 2. We saw that the ghost anti-ghost running in the loop, this diagram, canceled the contribution coming from the this pole at d equal 2. So when you sum all of them up, the pole at d equal 2 goes away, and we're all left with the log divergent terms that have this structure. So delta is m squared minus x times 1 minus xp squared for when the fermion runs in the loop. So m is the mass of the fermion, and when you have the ghost anti-ghost, which are massless running in the loop, or the gauge boson running in the loop, they're also massless. This is what delta is. Putting this all together, and extracting the divergent piece, it looks like, again, diagonal in the gauge indices. This is a structure we've seen before, transverse and G squared, the pole at D equal 4, and then C2 of G, which is the coming from the G is adjoint representation 5/3 minus 4/3 NF, the number of fermions that run in this loop with the minus because these are fermions running, and then T of R, which is the representation of the, which is fixed by the representation of the fermion. If we take them to be fundamental, anti-fundamental, then this would be half, right? All right. So delta 3 will have to cancel the divergences in the propagator. So this term at some scale. So we have a normalization condition and renormalized perturbation theory that will tell you that this term will have to vanish, right? That means that delta 3 in essence will have to be basically what we just calculated for this diagram at the scale m squared, right? M squared times 2 minus d over 2. So this is the renormalization scale, right? We saw, and then as we said, as we saw in the past, because of the renormalization condition, at the scale of interest m squared, we want the propagator, the correction to a propagator, one loop correction to propagator disappear. Therefore, delta 3 will have the m dependence. So it's a thing that will cancel the divergences at this scale. And if you recall, beta function comes from mddm, which means that all that we need to care about is just delta 3, because that's the only thing that it depends on m squared. The fermion self-energy, the diagram looks like this. This is the thing that has the pole at d equal 4. Now, the gauge boson is a loop, so this is massless. The delta is massless, right? There's a d minus 2 here, and x1 minus x, and this has to do with the fermion representation. Q slash Ig squared. This is the external x, right? All right. Once we look at we try to extract out the external piece of the log divergent piece of it. This is what it looks like. From this, you could fix delta 2, because at m squared, delta 2 will have to cancel this. So it has to be minus g squared over 4 pi squared gamma function at the scale C2 of R. This is delta of 2. Then we have the vertex at one loop. Vertex at one loop, there are two diagrams. This diagram is Ig cube, Yg cube, because there are 3 vertices. C2 of R minus half C2 of G. So this part of it is something that takes a little bit of calculation to figure out. And then there is the gamma function, as usual, with the pole equal 4. The gamma, mu, and T of A are just implied by the kinematics. This diagram is also G cubed. It has C2 of G coming from this guy, and then gamma mu, the thing with the pole at D equal 2. The fact that the vertex counter term will have to cancel this, it means that putting these two together at scale m squared have to be canceled with delta 1, the divergent piece of it. So what delta 1 is this, right? So then in summary, we calculated delta 1, delta 2, and delta 3 and renormalized the theory at scale m squared. The renormalization conditions were written for the propagator of the gauge boson, for the fermion self-energy, and for the vertex, right? As were the case for QED. Now, to compute the beta function, in QED, we saw that to the lowest order, beta function is mddm of basically only the counter terms, because the only dependence on m comes from the counter terms because of the fact that we have normalization condition at order m squared at energy scale m squared. So again, over there, Ward identities told us that delta 1 and delta 2 will cancel. The same cancellation will be repeated for non-abelian gauge theory in one loop normalized perturbation theory. This is what it looks like. But all the 3 terms will contribute. So in plugging in for delta 1 and delta 2 and delta 3 that we just calculated, we find that the beta function is minus 2g cubed over 4 pi squared Ct of r, Ct of g. This is the adjoint representation of the gauge field. This is n, right, for SUN. And then C2 of R is whatever representation the fermions transform in, C2 of it, minus C2 of R plus half, 5/3 of C2 of G plus minus 4/3 NF T of R. These guys cancel, we're left with this. So notice, minus G cubed over 4 pi squared, 11/3 C2 of G minus 4/3 NF. NF is the number of fermions that lives in the loop, that run in the loop. This is pretty clear where this term comes from. It comes from the fermions running in the loop, TR. If NF is small enough, this term is positive, or if C2 of G is large enough, this term is positive, we end up with a positive, with negative beta function, which means that the theory exists in the UV. This is called asymptotic freeness. Asymptotic freedom. This means that the beta functions, it means that the coupling goes to 0 deep in the UV. It comes from 0 deep in the UV and grows in the IR. So compared to QED, C2 of G is 0. The reason is that the C2 of G comes from the, if you remember, the quadratic Casimir. The adjoint representation is basically FAB, FACD, FBCD, but in the case of U1, F's are 0 because the algebra is abelian, so the C2 of G is 0. This term goes away, and no matter how many fermions you have, beta function ends up being positive because T of R is positive. But in the case of QED, T of R was 1 and NF was 1. In that case, we found that beta of E is positive E cubed over 12 pi squared, right? So beta QED did not exist as a theory because beta function was positive. Now, it's pretty clear that the non-abelianness is responsible for a positive term, for the making the beta function or the beta function more negative and the theory well defined. So what's the physics of this? What's the physics of this term? What makes QED, the coupling of QED, to become smaller deep in the infrared? So what it is charge screening in QED. If you have some, so what is the coupling of QED? Is alpha is epsilon, E squared over 4 pi. So E is the charge of electron. So here is some electron. As you put this electron in the vacuum, this will form, the electric field will polarize, create these dipoles near it in the vacuum. You can think of this as vacuum fluctuations creating electron-positron, electron-anti-electron pairs, which are effectively contributing a dipole moment of length 1 over m. And we calculated this effective potential, the one loop correction to the effective potential. So it's minus alpha of R is the classical Coulomb potential. The one loop correction to it takes this form. And what happens is that you can see at larger and larger distances, the effective charge is smaller. That's what it means, or effective alpha is smaller. That's what it means for the beta function to be positive. So this picture of charge screening is still present in non-abelian gauge theories, right? It's pretty clear this is not present in non-abelian gauge theories. But if you have matter content, if you don't have any fermions, any fields coupled to the gauge field, then the whole thing comes from here, and that is, it's a negative beta function. That theory, pure Yang-Mills, has positive beta function, has negative beta function as well defined. But in general, there's a competition between matter and the gauge field, right? So why is it that the contribution of non-abelian gauge fields, the self-interaction of non-abelian gauge fields, is anti-screening? What it should do is that it should anti-screen the charge. When you put the charge, non-abelian charge, the effect of it has to increase the charge even enough to make up for charge screening. So charge screening is present, but now you should have anti-screening by a larger amount to cover that. So what's the physics of that? All right, we want to describe that in non-abelian gauge theory, fermions, as I said, still cause charge screening, but the gauge boson that run in the loop or the self-interaction of gauge bosons give you an opposite effect. So we're gonna argue for that, and to argue for that, let's just pick G equal SU2, the gauge group SU2, because it's the simplest case possible. Here's what the equation of motion is: d mu, the covariant derivative of F mu nu of A is the, as we said, F mu nu is not gauge invariant, so it's a gauge invariant. The Lie algebra valued field strength is G J nu of A, right? G is the coupling, and this is the current for the Lie algebra component A. We're going to do this in the Lorentz gauge and for SU2. So we were going to have F di of F0IA is G rho of A. This is the analog of the electric field, right? This is the non-abelian electric field, if you wish, and this is the non-abelian electric current. Of course, these are Lie algebra values, therefore they're not gauge invariant, as opposed to the electric field in U1 gauge theory in QED. So this is a covariant derivative, which means that there is a correction term that looks like G epsilon ABC. Epsilon ABCs, these are the totally antisymmetric tensor, and they're the FABCs of SU2. They're the structure constants of SU2. ABI and ECI, right? So I is a space-time index, and ABCs are gauge indices. So to see charge anti-screening, what we have to do is a little bit of a comparison. So consider the standard case of 1 over r squared. In the standard 1 over r squared, what we had is, by the way, this is a divergence equation. So this equation, if this term were not present, which is the case when there is no self-interaction, what you have is the Coulomb law that the divergence of EA is G rho A. This is 1 over r squared law for the Coulomb force, right? Electric force. But we want to see the effect of this term. That's what we want to do. So let's just expand this for A being 1 and 3. So there are 3 of them, right? 1, 2, and 3, because you have sigma x, sigma y, sigma z. These are the adjoint, these are the operators for SU2 generators in the fundamental representation. So this is what the component, what it looks like, right? So the divergence of E1 is the E1 charge plus something that depends on E3. And the divergence of E3 depends on, well, is the rho 3 charge and something that depends on E1. Now, what we're going to do is we're going to put only the rho 1 charge and no rho 3 charge. When we put rho 1 charge, that will create an E1 field around it. So here's what E1 field is. That E1 field will induce a negative E3 charge. So whatever sits on the right-hand side of this, if the theory with abelian were to be interpreted as a charge for E3. So the effect of turning on E1 acts as effective rho 3, right? So that looks like negative, effective negative charge for rho 3, which will source this guy, E3, negative charge, will effectively make the right-hand side of this guy smaller. This negative charge, E3, combines with A2 to give an, makes this guy larger, to increase rho 1. That's what the effect is, right? So rho 1 will create A1. That A1 will create an effective negative rho 3. So the direction of these guys are inwards, right? That's E3. E3 and A2 will combine to give you a positive rho 1. So you have to do the contraction, and it gives you a positive one. So this is anti-screening. Anti-screening is the origin of the fact that non-abelian gauge theory, the self-interaction of the bosons, results in anti-screening, and if it's large enough, it will win over the screening of charges, and it will result in a positive, as a negative beta function, the theory that exists in asymptotic freedom. So that's the physics of it. If there are any questions, it's now a good time to ask. All right. So what we're going to do in the remainder of this lecture is we're going to calculate the beta function that we just computed. Well, we didn't compute the beta function. We just calculated the, well, we kind of did actually. No, we computed the beta function. This is the beta function. We're going to calculate this using the effective action. So recall that we said in Calin-Semantic is the running of the correlation functions as a function of mass, as a function of scale. Now, we also said that effective action also satisfies an equation similar to Calin-Semantic, and then there's a beta function that we could extract from that. We did that for ON model. So we're going to do that. The reason I'm going to repeat this, rederive this beta function is that I'm going to use it using background gauge fields. First, I'll explain what background gauge fields are, gauge fields are. And on top of it, it will give you a better idea of how to generalize this to more complicated theories without really doing loop intervals much. All right, so imagine, so what is the sort of background field? So if you had some scalar field, when we talked about effective action, we said that, well, you could have a classical piece and you could quantize your field around a classical configuration. That's the 1-point function. You can do a similar thing and take a mu of A. Now I'm going to jump directly to non-abelian gauge theory and quantize it around some background field. Now these are the fluctuations that I'm calling a mu of A. Okay, this is the background. So you could here's something that comes up. You could think of this if this were QED or electromagnetism. You could think of this as some background electric and magnetic field. Electric and magnetic fields are physical. A mu has some gauge redundancies. So it's expected that this whole thing is gauge dependent. So that's going to be an important part of the story. But let's just proceed with this, right? We define a covariant derivative with respect to this background gauge field, which I'm going to denote by d bar. So d bar is del mu plus GFABC A bar, right? Contracted with whatever it is. So if this is the covariant derivative, the background covariant derivative is d bar mu acting on a mu, the fluctuation, this is the expression for it. So now this bar is not to be confused with that. This is just anti-fermion. So psi bar d slash d goes to psi bar d slash d. Now this d bar is the background gauge field, right? Plus psi bar gamma mu ta psi a mu a, and then f mu nu transforms in the following way. F mu nu goes to the background f mu nu plus d bar mu of a nu minus d bar nu of a mu a plus a term that is bilinear and the fluctuation. Are there any questions so far? All right. So now we have the gauge invariance. Under gauge transformation, the fluctuation transforms in the following way, right? The fluctuation will transform with the covariant derivative, which is I can write this way. So it's convenient to choose a gauge which is in the past what we're choosing was del mu of a mu of a minus omega a equals 0. Now we're going to choose a gauge choice, which is the covariant derivative, the background covariant derivative of a fluctuation is omega a. It's a gauge choice. I can do whatever I want. Then with this gauge, if you repeat the Faddeev-Popov, you get the following Faddeev-Popov Lagrangian: 1 over 4g squared, the classical field strength plus this is a term that looks like this looks like the derivative of the f mu nu for the fluctuations, but now standard derivatives are replaced by the covariant derivatives with respect to the background gauge fields plus a term which is bilinear squared, right? And then we're gonna get a gauge fixing term because of this, which is 1 over 2g squared c d bar a mu, right? So previously we had del mu a mu, now we have d bar, this is the gauge fixing term. We're going to get the kinetic term for the fermions, which has the covariant derivative with respect to the background. We're also going to have d bar here squared for the gauge field, for the ghost anti-ghost, and similarly for the coupling between the two, between the ghost anti-ghost and the gauge field. Any questions? Now, I said at the beginning that a background gauge field is not gauging, is not a gauge, it depends on the gauge. It's not a, to introduce a background gauge field, that's not necessarily physical because there are still gauge transformations, right? So these are the background gauge transformation. The result of our path integral is going to be a partition function for the background gauge field. But because of gauge invariance, it better be that the partition function with the background gauge fields has this symmetry, right? So now the partition function or effective action, the background gauge transformations act as a background symmetry for this partition function. Is that part clear? Are there any questions?
Can you repeat this thing? This.
Yeah. So let's think about QED. What is the thing that physically could be a background? What can be background physically are the background electric charge and background magnetic charges, right? Background magnetic fields. So that's what the physical background is. But to say you have a background gauge fields have redundancies, right? If you do a gauge transformation of your background gauge fields, you still have the same electric and magnetic background fields. So if you took the action, as I did, and split the gauge field into some background gauge fields from some fluctuation, you did the path integral over the fluctuations, the final result is going to be a functional of the background gauge field, but that functional, of course, is not quite physical yet because it has redundancies. There has to be this functional better not care about the background gauge field transformations because the only thing that's physical is electric and magnetic fields, right? So that's what this statement is. So this is what I just said is what we just went through is a non-abelian version of that.
Yeah.
Any question? Yeah. Does that help?
Yeah. Thanks.
Okay. Yeah. So to compute the effective action at one loop, we only need to keep terms quadratic in the fluctuation. We saw this in our analysis of the ON model, right? So all we need to keep is the terms of the quadratic in a mu, and then we're going to perform the integral for, again, a convenient choice, which is equal 1. All right, so what does the quadratic part of the, well, what does the quadratic part of the Lagrangian the Fediev-Popov Lagrangian that we found looks like when you do expand around the background gauge field. So there is this term. There's f bar mu nu squared. That's just a constant. It's just a piece that's coming from the background values. It's a constant, but it comes out of the path integrator because we're path integrating over the fluctuation. The term that is present, right? So this, what I'm saying is, there's this term, which comes out of the path integral, and it will contribute to the fact that the effective action is classical action plus quantum correction. So if you want quantum corrections, you just take this part that's second order in a mu. First order will get can be thrown away if there is one by integration by parts. So here is the next the first term, which is kinetic term. It looks like f mu nu, where derivative is replaced by the background gauge field covariant derivative. Then this is the background gauge field strength that are contracted with the fluctuations. And then there's d bar. This is the gauge fixing term, basically, that have pick c equal 1, right? That's why it used to be, so here used to be 1 over g squared c. Well, 1 over c here, because I've taken the 2 out again. So that c equal 1, that's the gauge fixing term, right? So now, using integration by parts, you can write this down as d squared. Remember that we're dealing with a non-abelian gauge theory. So d, both covariant derivative and the background gauge covariant derivative are matrices. These are matrices, right? So you end up with this term plus d bar mu, d bar nu, ab. This should be familiar from the propagator for a gauge boson, right? The propagator is going to be the inverse of this. In the moments, it's the inverse of this. And then there's this extra term that's coming from the gauge fixing at x equal 1. And this term also shows up here, right? Now, what you need to notice is that, first of all, these two terms combine to an f mu nu. Why? Because this looks like the commutator of d bar mu, d bar nu, these two terms. And this commutator for the background covariant derivative is nothing but the background field strength. So these two combine into f mu nu, which can be next combined with this term, right? So putting all of this together, this is the equation you find. You get 1 over, so the Lagrange, the second order term in your Lagrangian for the fluctuation is minus 1 over 2g squared, a mu c. And this is the, I guess, in the case of the ON model, we had the mass matrix, right? And here, this is what it looks like. So we had a mass matrix, there was a kinetic part. So here's all kinetic part and the interaction part. That's coming from ours, right? Now, what does this look like? If you pay attention to FABC, this term could be written in the following form. So this term could basically written as a J rho sig. This is, you take the structure of these guys. This term could be repackaged this way. That's just like a little exercise where J rho sigma is just this contraction of Kronecker deltas. Writing it this way is instructive because it highlights that this is nothing but the generator of Lorentz transformation on four vectors, right? Gauge field is a 4 vector. For when this is the contribution to the kinetic the second order term, right? And the action as we perturb around an background field, gauge field, for the gauge field. You also can do the same thing for fermions, where you have psi bar, and some operator that sits in the middle. What if you repeat that? So this is what it looks like, right? You take this guy and expand it. What you obtain for the second order term looks like this. And over here, after massaging it, writing in this form, what sits here is exactly of the same form. Now, what sits here is the Lorentz generator for spin half fields. What it looks like is actually exactly this. So this is the Lorentz generator for spin half fields. In general, what we have is that when you calculate the covariant background fields, if you have a field in representation little r and spin j, this is for gauge theory, right? For one of these non-abelian Yang-Mills, non-abelian gauge theory, Yang-Mills coupled to a bunch of fermions or some matter fields with index j, and then you do the Faddeev-Popov. This is what it looks like as a contribution of the diagonal. You expand the Faddeev-Popov action around the background gauge field to second order. This is what it looks like as an operator sitting inside all of these operator, as Gaussian integrals. This is the kernel of every Gaussian integral. So if you recall, so what we could do is, what we'll have to do is we have to perform a path integral over psi, the fermions, the gauge field, the gauge boson, the ghost and anti-ghost, then the Faddeev-Popov plus counter terms, right? So Faddeev-Popov plus counter term, the one loop pieces of the integral. So there's a part that comes out completely. This is the part that comes out completely. It depends only on the background gauge fields, and it's independent of the fluctuations. The rest of the integrals are Gaussian, right? Because it's just an operator sitting in between things. So the part that is this guy, this is if you perform a path integral over mu, this is some operator in the middle of it, right? What you're going to get is 1 over determinant of this operator, right? So here's what I'm going to write: determinant to power minus half, sorry. Determinant of this delta, this operator, right? This is delta. For the gauge boson, where G is the adjoint representation and spin is 1. Minus half comes from the fact that these are commuting variables and we're doing a Gaussian integral, right? Then you have the fermions. For the fermions, when you do anti-commuting variables and perform the Gaussian integrals, you get positive power of half. And of course, the determinant of the same object. So this is R is a representation of the fermion and spin is half. And you have NF of them. So this is the contribution of the fermions, sits in the numerator, and this is in the denominator. And then you have ghost, anti-ghost. Ghost, anti-ghost are complex fields, right? And they are both they're anti-commuting. Therefore, you get to the power plus 1 here. Spin is 0, and they transform in the adjoint representation. So this is the form of the effective action, path integral that we do. Well, exponential effective action. Exponential. This is the form of the partition function at one loop. Any questions? But you can now see that if you had matter fields of higher spin coupled to a gauge field, or some matter fields transforming in some other representation of the gauge group, all you need to do is just plug in the appropriate delta, whether they're fermionic, whether they're anti-commuting fields or not, inside the determinant, and that just is, in one shot calculates this. The reason that this is good is that this is nice is that there are a lot more. There are some theories that are more complicated than the gauge theory that we talked about, the non-abelian gauge theory, Yang-Mills that we've been talking about. These could be supersymmetric versions of them, and this calculation just boils down to, it's just kinematics. How many of what matter field do you have, right? What is the matter content of it? Describe to me the representation theory. This is fully representation theoretic. This is completely fixed by the representation theory. And we're going to see that the beta function is just dependent on this part. So if you want to calculate the beta function in some supersymmetric gauge theory with some matter content that's complicated, you don't need to go ahead and do the one loop, draw all the one loop diagrams, do one PI stuff. You could do that, but this is a shortcut. The effective action gives you a shortcut because there's a formula of this type. You just put in how many of what field you have and just plug in this delta in there. And we're going to see in a bit that this equation, well, we've seen it already before, will be enough to read off the beta function of the theory. All right, any questions so far? Okay. So this is the one loop action. The counter terms are here. And what we need to do is, what I'm going to do is, to compute the beta functions, we're going to go to the Wilsonian framework. And I try all sorts of different methods as we do for different calculations, the methods that we've discussed, to provide a variety of ways of doing this calculation. It's not the only way of doing it. So what we have is that, imagine we introduce a momentum cutoff at scale lambda. So you get a cutoff. So imagine that in the Wilsonian framework, this is what your, so you don't have these terms at all. And your, at scale lambda, this gamma is just coming from this interval, where g squared is now g squared at that scale. As we integrate down from scale lambda to scale m at one loop, what's going to happen is that this guy is going to be still an integral of the background gauge field, but with a new coupling, right? The coupling will change. How will it change? It will change with log of m over lambda, because we saw there are log divergences. That's how their running works. And this is what is the new coupling at scale m is, right? So is that step clear? So this is what we found when we did the a narrow, a thin shell path integral in Euclidean momentum, and the Wilsonian approach. So all I need to do, in a sense, is look at this term, this correction, one loop correction, and isolate the piece of it which is proportional to the background f mu bar squared. Once I isolate that term, how it depends on how it shifts this 1 over 4g squared, the shift will encode this coefficient, will encode the beta functions. Is that clear? Are there any questions? So you see now these determinants, I pull them up and put them in the action as, so log of, this is half, was because this was a gauge field, had to a power of minus half. These were Gaussian variables. Log of the determinant, right? Log of the determinant, nf over 2, these are fermionic, so that's plus, right? Delta of r and half, and then log of the determinant, these were again fermionic, so plus. This has to do with the ghost anti-ghost. Questions? All right. To find beta function, as I said, what we need to do is need to take this log determinant and expand them in powers of f bar, the background field strength, and isolate the piece that's f bar mu a squared. So you take log of the determinant, and these coefficients are what we want to read. I put the 4 separately, well, because of just it's a convenient thing. Because we're gonna look at the contribution of this to, it has to take this form, f mu bar squared over 1 over 4g squared. So that 4 I isolate separately. So if the log determinant, if the coefficients CR, J are defined this way, then the running of the coupling will be as follows. So it would be 1 over g squared plus half CG1. This is the contribution coming from the gauge boson in spin 1 and the adjoint representation, minus CG0, right? CG0 is the contribution of adjoint scalars. These are ghost anti-ghost, minus, because this power was negative, this power was positive, and then minus nf over 2 CR half. This is the contribution of the fermions running in the loop, right? The fermions are in some, they're spin half and they're in sub-representation little r, and there are nf of them. Minus is because they're anti-commuting. So this is what it looks like. Now, of course, CRJ is going to be log divergent. We're isolating the log divergent terms. However, well, therefore, structurally, this is what it looks like. They look like log of m squared over 2 squared. This is what structurally it'll look like, right? So if you want to compute the beta function, what you need to do is do MDDM of G of M. We calculate just G of M. G of M would be this, right? So if you do that, what you're going to find is that, well, there's this log of M squared in every single term. MDDM of that will basically tell you that the beta function is half C tilde, which is the whatever is CRJ, the coefficient of CRJ that's proportional to log of M squared over Q squared. C tilde G1, C tilde G0, and C tilde R half. This is the contribution of fermions to the beta functions. This is the contribution of the Gauss anti-Gauss, and this is a contribution of the gauge boson. All we need to work out are C tildes. But C tildes were all kinematics. They're just like what kind of matter of what spin and what gauge group, what representation you have. And here's the answer for it. So in some representation R, sorry, this is C tilde. In representation R and spin J, this is T of R over 4 pi squared. If the spin is scalar, spin 0 is third. If it's a Dirac spinner, minus 8 over 3. If you have a 4 vector, spin 1, so this is spin 0, half is minus 20 over 3. And more generally, you could also calculate what this is as a function of spin. So this would be J0, J half, and J1. All right. So now we put all of this together. What do we find? We find this, that beta function will be, so what do we have? This guy is minus a third. This is minus a third. The C tilde of G1 is going to be minus 20 over 3. There's a half that you put here. And then there's T of R has to do with the fermion. So T of R is here, and this is T of G because these two guys are transforming the adjoint. So this is T of G. This is T of R for the fermions, NF of them, minus sign, and the fermions, will each of them will give you minus 8 over 3. There was a half here, that's half. So this piece will give you minus 4 over 3. This piece will give you minus 11 over 3. So the Gauss anti-Gauss combine with the gauge field to give you, so there's a, so I'm taking the minus out, minus G cubed over 4 pi squared, 11 over 3 C2 of G, minus 4 over 3 NF T of R. So now this formula gives you exactly what the beta function is in terms of the number of fermions that transform in some representation R and the gauge group, this is the adjoint, right? So if you are dealing with SUN with fermions in the fundamental representation, so first of all, if you take pure Yang-Mills, NF is 0, so beta function is negative. Pure Yang-Mills is a sensible theory. It has negative beta function, it has asymptotic freedom. When you add fermions, so pure Yang-Mills has anti-screening. When you add fermions to create screening, if the number of fermions is not large enough, every fermion that you introduce, they contribute a certain amount of screening that reduces the total amount of anti-screening. If you introduce too many of them, the beta function will become positive, and the theory will be ill-defined. Well, will not exist. That's the case of QED, where there are no non-abelian interactions. So this term is 0. So no matter how many fermions you have, you end up with a positive beta function. The theory has Landau pole and is ill-defined in the UV. But if you are in the SUN gauge field, and the fermions in the fundamental representation, this is 11 over 3 n minus 2/3 NF. So if NF is less than 11 over 2n, beta function is negative, the theory is well defined and good. So these theories exist. If n is equal to 2, then NF is bounded above by 11. So SU2 gauge theory coupled to up to 11 fermions. That theory has negative beta function, it has asymptotic freedom, it's well-defined. If you have 12 fermions, that theory is ill-defined. It's too much screening that will make the theory ill-defined in the UV. For n equals 3, which is a case of interest, the number of fermions up to 16 is okay. So SU3 is a gauge group that will be important in the standard model, and so does SU2. So for number of fermions less than 16, this theory is also safe. Beta function is negative. So in summary, this is an important equation you should have in mind. We computed the beta function of Yang-Mills coupled to matter fields, right? Using one method was calculating it using the doing the one loop. Well, we normalized perturbations here at one loop. We calculated one loop diagram, one PI diagram. There was a gauge boson propagator, 6 diagrams, 6 diagrams contributed to it. We did the calculation over there. We normalized it. We found, and then we did the vertex correction. There were 2 diagrams. There was a fermion propagator correction. That was 1 diagram. We did all the calculation. We summed them all up. We had 3 counter terms. We ate all these infinities at scale m squared in the counter terms by the normalization condition. Once we did that, now we can just take the counter terms and take derivatives to find the beta function that we had shown before. And we did the calculation, we found this formula. That seemed like a pretty detailed formula with a lot of structure of the details of the one loop intervals. We repeated this calculation in a different way. Using it, we did the calculation in a different way by introducing a background gauge field. What it was nice about the background gauge field, so effective action of one loop, only depends on the kinetic piece. So what we introduced was a background gauge field. We expanded around it. There are fluctuations. We took the Fediev-Popov, expanded it to second order fluctuations. There were kinetic terms for the gauge field. For the fluctuating gauge field, there was kinetic term for the fluctuating for the fluctuations of the for the ghost anti-ghost, because there's no background for them. And then there was the kinetic term for the fermion anti-fermion, and each of them contributed just by a differential operator that we repackaged in this form. What is elegant about this is that we actually can write down this differential operator in your favorite representation theory and favorite spin in this form. So any theory, now you don't need to do one loop intervals and the way that we've been discussing. Any Yang-Mills theory coupled to any form of matter in some representation R, the matter has spin J, doesn't matter. Then you take this expression. Once you do the one loop integral, you get an expression like this for different representation R matters of different spin will contribute to the determinant. If they're fermionic, if they're anti-commuting, the power would be positive. If they're commuting, would be negative. Sorry, if they're anti-commuting, if they're commuting, it would be negative. So like this, the gauge boson, right? For Yang-Mills, there's always this term, which is the ghost anti-ghost, and the gauge boson. This has positive because they're commuting. They're anti-commuting, and this is negative. These 2 terms gave us these 2 terms, right? These 2 came from the gauge boson and the ghost anti-ghost. So we're separating the matter content, contribution of matter content. We can nicely separate the contribution of matter content. The fermions that run in the loop, they don't have to be fermions. There could be other fields that run in the loop if they're coupled to the gauge field in whatever representation they are. Their contribution comes from this term. So in the case of fermion, is NF, because every fermion, well, they're anti-commuting, right? The minus sign in the loop will tell you that there's a positive coefficient here. To compute the beta function in the second method, I didn't want to do renormalized perturbation theory, so I did a Wilsonian, where is it? Here, Wilsonian framework, and I did a thin momentum shell integral. That changes the value of the coupling from 1/4 g squared to something that's shifted by a log of m over lambda. This is a log divergent terms, but we're just doing an infinitesimal transformation, so we could isolate it this way, right? If you wanted to see this, what you do is you first write down these determinants, you pull them up to the action by taking the logarithm of it. So you get log of determinant of this operator, log of determinant of this, log of determinant of this, right? The piece that could be interpreted as the running of the coupling is running of the coupling if it's a coefficient of f bar mu nu squared. So in these terms, all that we need to care about is the coefficient of f bar mu nu squared with a coefficient 1,4 coming out, so that this can be naturally interpreted as how much 1 over g squared has changed. Now, of course, there are log divergences here, but now the log divergence has the form of log of m squared over q squared. So the only thing, because the beta function will be mddm, it will only capture this term. So we could nicely write down the beta function in terms of this tilde. So this is the tilde thing coming from the gauge field, the adjoint spin 1, adjoint spin 0. This is the ghost anti-ghost and the fermions and f of them. And we can just like directly calculate using the fact that that operator delta of rj is a known operator. We wrote down explicit expression for it when representation r and spin j. We could calculate these guys explicitly, so we get T of R over 4 pi squared. Of course, it depends on representation. For spins, I just wrote 3 cases. J equals 0, scalar is a third. J equal half is Dirac spinner is minus 8 over 3. And J equal 1 is the 4 vector minus 20 over 3. I just wrote these down because these are all that I need for in Standard model for fermions coupled to gauge boson. That's all I need. So the ghost anti-ghost combined with the gauge field gave you this anti-screening factor, minus 18 over 3. The whole thing is negative in the beta function, so it's anti-screening. Whereas the fermions give you this positive 4 over 3 TR and F. That is screening, right? And the whole thing can be packaged, if you pull out the negative sign here, as a competition between the gauge group and the fermions. And we said that in pure Yang-Mills, this term is absent. C2 of G and SUN is N. This is positive. Well, actually, in any representation, this is positive. Therefore, beta function is negative. Pure Yang-Mills as a theory in 4 dimensions exists. Beta functions are negative. The theory is so-called asymptotically free. So what went wrong with QED? QED was the case when you had NF, so that was screening, but your gauge field was a billion, so this term was absent, so beta function was positive. That's what went wrong with QED. And it didn't matter how many fermions you had. You just had no anti-screening. Everything was screening, therefore that was bad. Now in SUN, there's a competition between the number of fermions and the gauge fields, right? And the gauge group. In SUN, if the number of fermions is less than 11 over 2 of n, then this theory exists. It's a really neat observation. Yeah, I'm going to stop here. Are there any questions about this lecture? This is the end of this lecture. All right. If there are no questions, I will see you guys on, I guess not Tuesday, because next week is the spring break. Next lecture would be the week after. All right. Thank you so much.
I had a quick question.
Yes.
So you did this for Dirac spinners. Would this change if you had like a Majorana or?
What would change? Actually, you could guess. So I gave you the full answer, right? The full answer is this object. So this is the Lorentz generator for your spinner. Right? So you just plug in the Lorentz generator for your spinner. Where does this come from? Right? This is the Lorentz generator for the Dirac fermions, right? So you know how to chiral fermions would involve projections to the left hand, right hand movers, right? So you know how to replace this. This is the full expression for it.
I see. Oh, okay. Okay. So you just replace that with the Majorana. Okay.
Yeah.
Gotcha.
All right. Any other questions? If not, thank you so much. Bye, guys.